So this is another example of a constant coefficient problem, a second order constant coefficient differential equation. We're going to assume the same kind of solution, but this problem is going to be a little different because this involves repeated roots. And so we're going to talk about how to obtain the second solution, and then we're going to verify that that solution satisfies the equation. So just like with other constant coefficient problems, we're going to assume the form of the solution to be e to the rx. And then, of course, our derivatives are r e to the rx, and y double prime is r squared e to the rx. And when we substitute these into our problem, e to the rx plus 18r e to the rx plus 81 e to the rx, we get an equation that has e to the rx everywhere. And so when we factor that out, we get our characteristic equation that we can solve in order to obtain a solution for r. Now, in this case, this is a perfect square. 81 factors as 9 and 9, which add to 18. And so this is r plus 9 squared. And so we only obtain one solution, which is r equals negative 9. Now, as I noted, every second order equation has to have two solutions, not just one, and this is only one. So we know that the first one is going to be e to the negative 9x. But how do we get the second one? Well, and this is something that we can verify if we use reduction of order, which I will save for another video. But the trick that we're going to employ all the time with constant coefficient problems is we're going to multiply the original solution by x. And so what we want to do, not just state this, we want to verify that this is in fact the case. So the first thing we're going to do is we're going to show that these are in fact independent. So we have e to the negative 9x, and the derivative of that is negative 9 e to the negative 9x. And then this one is x e to the negative 9x. And the derivative of this requires the product rule. So e to the negative 9x minus 9x e to the negative 9x. So derivative of x is 1. Copy the second function. The derivative of e to the negative 9x is negative 9 e to the negative 9x times the first function, x. And so if we can then calculate the determinant, this times this, we get e to the negative 18x. That's this one times this one, minus 9x e to the negative 18x. Because negative 9 and negative 9 add to negative 18. And then minus, we'll flip this sign again to a plus, e to the, and then negative 9 and negative 9 will give me negative 18x. And we can see that the x, e to the x terms cancel, and I'm left with just e to the negative 18x. Which is what we would expect. And again, if you switch the order of these in the matrix, you will get possibly this answer with a negative sign. So they are independent because this answer is not 0. And so what we also want to do then is we want to verify that this does satisfy the equation. So if y2 is equal to x e to the negative 9x, and y2 prime is equal to, and we just found it here already, so we'll just copy it. And then y2 double prime is going to be, well, negative 9, e to the negative 9x. So that's the derivative of this term. And then the derivative of this term is going to need our product rule again. So negative 9 times the derivative of x is 1, e to the negative 9x. And then the derivative of, we just keep the x, but then the derivative of e to the negative 9x is going to give me another negative 9 e x e to the negative 9x. And of course, we can see that these two things add together, be 18, negative 18 e to the negative 9x plus 81 x e to the negative 9x. Negative 9x. Okay, and so we plug these into our original differential equation. So our second derivative was this. And then we had 18 times the first derivative plus 81 times the original function. Well, let's see what happens. So we've got negative 18 e to the negative 9x and 81 x e to the negative 9x. But then we have plus 18 e to the negative 9x from this term right here. And then we have 18 times that. Well, this is 9 and 2, so that would be negative 81 times 2 would be negative 162 x e to the negative 9x, and then plus 81x e to the negative 9x. And so let's see what cancels. So negative 18 e to the negative 9x and positive 18 e to the negative 9x. That cancels. And here we have 81x e to the negative 9x and another positive 81x e to the negative 9x. And 81 and 81 make 162, and this is the negative version. And so this does, in fact, simplify to 0. So this second solution, modifying this first solution by multiplying by x, does, in fact, produce a second solution that also satisfies this differential equation. And so, therefore, we know that our final solution, y of x, is c1 e to the negative 9x plus c2 x e to the negative 9x. And so those are our two independent solutions that both satisfy the equation.